For years, AI content moderation relied on a rigid blueprint. Developers built fixed hazard taxonomies, lists of specific harms like hate speech or violence, and baked those rules directly into a safety classifier's weights during the training run. If a company needed to change those rules or adapt to a new threat, they had to rebuild the system. Updating the built-in policy meant undertaking a time-consuming and expensive model retraining process. This static approach fails in production. A strict safety taxonomy designed to protect users on a mental health platform will overly censor and break a cybersecurity research tool analyzing the exact same text. The industry is attempting to bypass this bottleneck. Instead of hard-coding the safety policy during the training run, engineers are pulling the rules out of the weights and dropping them directly into the inference prompt. This allows deployers to write, tweak, and A/B test their safety rules on the fly, using plain text without training a single parameter. This structural shift transforms moderation into a dynamic, deployer-controlled question asked at the moment of inference. Mistral released their specific vehicle for this shift, Shieldstral. It is a 3 billion parameter open-weights multimodal safety classifier. Because of its size, it runs locally on a single 16 GB GPU, and it ships under a highly permissive Apache 2.0 license. Mistral's primary marketing claim is aggressive. They state this taxonomy-free 3 billion parameter model matches or outperforms specialized guard models up to 7 times its size. To evaluate that claim, we need to decode the mathematical mechanism making this possible, price out the actual deployment costs, and dissect a notable discrepancy between the press release and the benchmark data. These Mistral's numbers hold up. Shieldstral suggests that in the realm of safety classification, the training recipe can outweigh the parameter count. Shieldstral discards standard multi-label generation. Instead, it requires a strict prompt template comprised of 3 parts: an instruction context, the user document being evaluated, and a query. The query has a structural limit. It must be phrased as a single yes or no question. Abstract labels or keyword lists are forbidden by the architecture. Rather than generating a conversational response, the model evaluates the input and reads out only the raw yes and no logits from a single token prediction. Those 2 extracted logits are then passed through a softmax operator. The softmax operator converts the raw logits into a continuous safety probability score between 0 and 1. Because the score is continuous, the model shits with no default discrete label. You decide where the cutoff is, leaving the false positive and false negative threshold entirely up to the deployer. This mathematical formulation unifies distinct tasks. Prompt classification, response moderation, and refusal detection all run through one identical pipeline. The WildGuardTest prompt classification benchmark serves as a reliable proving ground for Shieldstral's performance. This chart shows how the models compare. Shieldstral 3B posts an 88.1 F1 score. When compared directly to GPT-oss-safeguard 20B, the much larger model scores an 87.3. A 3 billion parameter model beats a 20 billion parameter model on its fixed taxonomy home turf. To test the assumption that more parameters automatically buy better safety, we can look at ShieldGemma 9B as a control subject. ShieldGemma 9B experiences a drop in performance, scoring only a 46.0 F1 on the exact same test. The fact that a 9B model fails to track between a 3B and a 20B indicates that in this specific regime, the training recipe is more critical than the sheer size of the model. For engineers pricing out the adoption of this stack today, there is a distinct economic reality to consider. The architecture has a catch. Because the model processes one specific yes or no question at a time, evaluating multiple rules requires sequential discrete checks. If you want to run a 10-rule safety policy against a single user document, you must execute 10 complete forward passes through the model. The efficiency of a single forward pass only holds true for deployments that can condense their entire safety policy down to a single binary question. The official press release headline claims Shieldstral matches or outperforms OpenGuard models up to 7 times its size. The announcement's charts rely on formatting that omits access values, data labels, and baseline names. The actual numbers buried in the Hugging Face model card tell a different story. Qwen 3 Guard 8B edges out Shieldstral 88.2 to 88.1 on the WildGuardTest. On the OpenAI moderation benchmark, the 20 billion parameter GPT-oss-safeguard model beats Shieldstral 84.0 to 81.4. The phrase up to 7 times is doing heavy lifting in the press release, considering the only baseline that size is precisely the model that beats Shieldstral on the OpenAI benchmark. A 3 billion parameter model being highly competitive, but losing specific rows to larger models is a strong result. That reality was massaged into an absolute victory by hiding the true evidence one click away. Forcing strict plain text policy prompts introduces a new failure surface. Current benchmark suites only validate fixed questions against fixed datasets. They leave real-world deployment variance unmeasured. There is zero published data on how the F1 score fluctuates when a trust and safety team rephrases or paraphrases the exact same policy question. The model card explicitly concedes weaknesses in handling obfuscated inputs and adversarial attacks targeting the yes-no logic. If the classification accuracy degrades based on how the deployer words the question, the freedom of inference time policy collapses back into relying on fixed vendor-tested prompts. If you require data-driven analysis of AI architectures the moment they launch, subscribe to the channel. Recently, we covered the Kimi K3 model, where 2 governments proved that safeguards baked into open weights models cannot resist deliberate removal by the operator. Shieldstral is the industry's structural answer to that failure. It abandons internal safeguards entirely, moving the safety mechanism into a discrete, external classifier. The catch of this externalization is that Shieldstral is also an Apache 2.0 open weights model, meaning running it alongside a base model is voluntary. In the open weights landscape, safety functions as a deployment choice rather than an inherent model property. Shieldstral protects platforms that want to be safe, but it offers zero resistance against an actor who simply chooses not to deploy it.